Welcome back to Physics Notes. So far in our videos, we've talked about our most basic vocabulary terms. Video 2 was about Newton's laws of motion. And now what I'm going to do is I'm going to breeze through some more vocabulary. Some of it might be, the explanations might be a little light, but we will use these things in depth so you will get a very good understanding of what I'm talking about after you understand the vocabulary. So first of all, vector. We've already described a vector. A vector is a mathematical quantity that requires 2 numbers to describe it. There's mathematical quantities that require 3 numbers as well. Those are called tensors. In physics, we're normally dealing with vectors. And specifically, those 2 numbers that are used to describe it, we use magnitude and direction. So to describe a vector, we've come up with a very useful and clever mental tool and visual tool. We use arrows to describe the vector. So the magnitude is the length of that arrow, and the direction is the way it's pointing. So you can see both of those numbers with one visual thing. Now, using the arrow is very useful because arrows are straight lines, they're not curvy, and vectors are straight lines and not curvy also. So don't think that a vector can be curved or something like that. They're straight line arrows. Now, vectors are useful because they can add. If I am, for example, on a bus and you are on a street corner and you are looking at me, so here's a big old bus. There's lots of windows in this bus. Let's say you can see me nice and clearly, and that's me inside the bus. Hello. If the bus is moving with a velocity of 5 meters per second to the right, and I am walking forward on the bus with a velocity of 1 meter per second, I'm walking towards the front of the bus, you can simply add those 2 velocities together to see how fast I would be appearing to move from an observer standing on the street corner. So you would take that 5 meter per second vector, and you would add that 1 meter per second vector, and you would wind up with a net velocity for me of 6 meters per second to the right. All right. The same would apply if I was walking instead to the back of the bus, but now this vector would be pointing the other direction, and if you put them head to tail, so that's the 5 meter per second one, and then I draw the 1 meter per second one back that way, this region right here is effectively canceled out, and what I'm left with is a net of 4 meters per second to the right. So the arrows are not just because we're weird and I like to make big arrows to point at people, but because they're a very useful mental and visual tool to understand vectors. The same thing applies for forces. So if you have a block on a table and you have the weight of the block pulling it down, let's see, there's a table, and you have the force of the table pushing it up, you can see that those 2 vectors are equal in length, opposite in direction, so the net force on that block would be 0. Okay? Dimension. This is just a review of mathy kind of stuff. In physics, we're generally talking about reducing things down to 2 different dimensions. You have the x dimension and the y dimension. And when we start talking about vectors, you can describe something as having a positive x value. Well, you define what dimensions you're talking about. So the standard way of doing it is something like this, where you say to the right horizontally is positive x, up is positive y, down is negative y, left is negative x. But you can really describe those however the heck you want to. And if you think about it, there's an additional dimension, which we normally try to kind of eliminate conceptually by looking at problems in 2 dimensions, but that is the z dimension, which is in and out of the page. So our arrow terminology and mental picture kind of comes in to help us out there. If you imagine a better arrow, so let's say I draw an arrow like Stephen Amell from the show Arrow might shoot at his enemies. You've got feathers on the back, you've got a pointed cone on the front. If you think about what this would look like if it was the z dimension, if it was coming out of the page, like my pen right now, you can see that you would see the tip of that point. So to show that, you can't really draw the arrow in a 3rd dimension, but you can draw what it would look like if it was pointing at you. So that would be z out of the page. And then if you flipped it around instead and it was going into the page, and you imagine there are feathers on the back of my marker, you would now see the X from the feathers. So this is how you show a vector going into the page. So that would be Z into the page. These types of, we won't really use in and out of the page a whole heck of a lot until second semester when we get into electricity and magnetism, but it's not bad to understand now. So dimensions, you have X, you have Y, you define what those are. If it's useful for you in a problem to define them like this, where you say that's positive Y, that's positive X, there's absolutely nothing wrong with that. You get to define what dimensions you're talking about, but those dimensions will matter, so make sure you do that. Okay. All right, other vocabulary. Weight is a force, and specifically, it is the force due to gravity. And we know that forces are described in terms of mass and acceleration. That is what Newton's second law teaches us. And for the force due to gravity, well, gravity is an acceleration. It's a warping of stuff that results in acceleration. So weight is equal to an object's mass times the acceleration due to gravity. And we can abbreviate that as mg, where g is 9.81 meters per second squared in most parts of the world, but you can quite simply approximate that to be 10 meters per second squared. And using 10 is not only allowable, but it's what I recommend unless you're doing a lab where you're looking for something very specific. But even then, you can still use 10. It's acceptable on the AP exam, and a lot of times it eliminates the you having to use a calculator. Now, the normal force is the force of an object when, let's say, you have a box on a table. Well, the weight of the box is pulling it down. The table resists that object moving through it and breaking through. So the normal force is a force that results from an object resisting something breaking through it. Sorry, I'm getting a little messy here. So it's a force caused by a surface resisting something breaking through it. The word normal actually means perpendicular. So the normal force is always perpendicular to the surface that's causing it. So in this case, if you have our box sitting on the table, the normal force would be perpendicular to that surface. So it would make a right angle right there, be straight up, and you would call that the normal force. If you instead have a box on an incline, on a ramp, now the normal force would still be perpendicular to the surface. It is always perpendicular. Remember, that's what normal means, perpendicular. A lot of times people make the mistake of equating this with weight and think it's always equal to weight or something. It's not. If you have a wall and you push a box against a wall, so you apply some force to hold it against the wall, well, the normal force, again, is perpendicular to the surface. It's just the wall resisting that box breaking through it. Now, tension is another force. Tension is generally something that you see when you have a string and maybe a pendulum or something hanging down through it. Tension is the force in that string. So it can only act in one direction, really. It can act along the string. So if the string is up and down, the tension has to be up or down. If the string is horizontal, let's say you have something with a pulley and you have a rope attached to a wall hanging down and there's a mass hanging right here, well, you would have tension in this string. It would be pulling up on the box and it would be pulling this way against the wall, but you can see that regardless, the tension is always in the string. So basic definition of tension, it's a force that acts in a string, rope, chain. Could be a solid rod. You'll learn more about tension when you study engineering, but for our purposes, it's the force inside a string. I use the letter T when I describe tension to abbreviate it. Static friction. Friction is a force that opposes the relative motion of two objects. So if I have a block on a surface, and let's say that block is moving with a certain velocity, friction is a force that tries to oppose that velocity, that sliding between the surfaces. And the reason it does that is because if you were to zoom in on those surfaces really, really big, you would see that the bottom of the box, even though it looks smooth to us, is actually bumpy, and then the ramp itself or the surface it's on is actually bumpy. So it's kind of like two pieces of sandpaper sliding past each other. So those things are going to want to lock in place, and they're going to resist sliding relative to each other. So that's what static friction is. It's a force that resists the relative motion of two objects in contact. So this is the basic definition of friction itself. Now you notice that this one is static friction, and what static means is those objects are not sliding. There is no relative motion yet. Okay, so if this is a block on a surface, this block and this surface are not moving relative to each other. That's static friction. So this example where I said the block is sliding would not be static friction. That would actually be kinetic friction. Kinetic is when they are moving. So for friction, you have the same definition for either one of these definitions for the friction part, but for the static or kinetic part, it depends what the object's doing. If it's static, the objects are not sliding relative to each other. If it's kinetic, they are sliding relative to each other. Now, both of these have equations that we figured out to describe them. So the force of static friction, I'm going to use the small letter F and the little letter S as a subscript, is always less than or equal to the coefficient of static friction, which is that little Greek letter, which I'll talk about down here, times the normal force. So you don't know, this isn't really an equation, this is an inequality, but you know that this is always less than or equal to this times this. So there's a maximum value to it, but it could be as low as 0. Now, kinetic friction is easier because kinetic friction is an equation, and it's equal to the coefficient of kinetic friction times the normal force. So once things are sliding, friction is pretty much a pretty much a constant thing. When they're not sliding, though, it could be as small as 0, but it could be as big as this. So there's a range, and usually have to figure out some way of finding what the value is besides just using that inequality. So what is this little letter right here? That's the Greek letter mu. And the way you say that is like mu. Like that, okay? Mu. Now, it's a property, or it's a constant value that is determined by the properties of the materials that are sliding. So if you took an object that are interfacing with each other. So if you took an object with a very, very rough and another object that's very, very, very rough, you would have a high coefficient of friction. If you tried through great lengths to smooth those out as much as possible, you would have a lower coefficient of friction. But it depends on these two materials, and usually you can find those experimentally doing a lab. I will tell you that for any two given materials, almost universally, the coefficient of static friction is greater than the coefficient of kinetic friction. So that means, and you might have experienced this when you're trying to move something heavy, it's always a little bit harder to get it to start sliding. Once you get it sliding, it's a little bit easier. Well, that's because the coefficients are smaller once it's sliding, and it's easier to move. This reduces the force. So this force is generally going to be smaller than the maximum value of that. Equilibrium we've talked about. Equilibrium means that the forces acting on an object sum up to 0. The net force equals 0. Now, this doesn't mean there's no forces acting on it. You could have an object like a block, and I could draw the forces acting on it. You might have a force from me pushing it. I'm going to call that F. You would have the weight of the block. That would be down. You would have the normal force, which is always perpendicular to the surface. And then let's say there's friction on the surface and it's sliding or it's at rest. You don't really know based on looking at this, but you can see that friction in this case is equal to the force that I'm applying. The weight is equal to the normal force. So the sum of the forces is 0. That object is in equilibrium. And all that means, if you think about it, is if there's no net force acting on it, there will be no acceleration, which means no change in motion. Biggest misconception people make is they think that means it's not moving. That's not true. This box may very well be sliding along, but it's definitely sliding along at a constant speed. It won't speed up, slow down, or turn because there is no acceleration due to the fact that there's no net force. Static equilibrium is just the special case of equilibrium when the object is at rest. That's all it is. No big deal. It's just at rest. Now, free body diagram is one of your most useful tools. You will become a master at drawing free body diagrams, and it's quite simply, it's a diagram showing all the forces acting on an object. And I would like to draw attention to the fact that those are on the object, so the forces that that object is exerting on other things do not get drawn in the diagram. A force resolution diagram is a little bit different. So let's say I have a free body diagram, or an FBD, of a block on a ramp that makes an angle theta with the ground. I could start drawing forces on this diagram. So you have weight, which is mg. You have normal force, which is perpendicular. And now, if I don't tell you any other information other than I say that this block is at rest, looking at this, I know there must be another force, because if these were the only forces, they don't cancel each other out because there's a component in this dimension up and down the ramp that's not being balanced out. So I'm going to go ahead and say that there's friction between the surface, and looking at the free body diagram, you can see there must be a force pointing up this direction to balance out part of the weight that goes along the ramp. So this is an example of a free body diagram. A force resolution diagram is where you show the components of the forces. You can call it free body diagram version 2.0. The components of forces are shown. And what I mean by that, if I just transfer this image, right? So I had weight. I'm going to make it a little bigger. I have normal force. And I have friction. In this case, static friction. What you're going to want to do is break one or more of these down into their x and y components. The easiest way, in my mind, to do this is to define your dimensions. Let's call this positive x. Let's call that positive y. So I can figure out what angle that is. And if you look at this diagram and you figure out what that would be, those two are equivalent angles. So that means that's theta, which means that this dotted arrow is mg cosine theta, and this is mg sine theta. Now, the reason that you have two different things, this is a force resolution diagram, this is a free body diagram, ignore that little dotted line, that's not there, is because on the AP exam, when they say they want a free body diagram, they do not want to see components of forces. They just want to see if you know what forces are acting and which direction they're acting. The force resolution diagram shows the components of those forces, which is significantly more useful for you mathematically when you start working a problem. So those are your vocabulary terms, and we will dive into, in our next video, a little bit more applications and misconceptions. Thank you.